Hello dear students, again I am available with a new presentation related to boiling and condensation. Well friends, we know that whenever latent heat is involved, in that case there is a phase change. If we are talking about sensible heat, then sensible heat can be sensed on TS diagram. But whenever we are talking about latent heat cannot be sensed on the TS diagram. It is a horizontal line. So, whenever we are talking about a phase change in the liquid, means convection heat transfer is predominant and we are talking about convection heat transfer at present. So when there is a phase change means two different modes are available, and from the convection heat transfer coefficient point of view, that value of H is very high, that is more than 10,000 watt per meter square degree Celsius. So in this chapter we have to consider the phase change between liquid and vapor. Whenever the liquid is boiled and that is converted into vapor, it is called boiling process. And whenever the vapor that will be condensed and it will form the liquid, it is called condensation process. So now in detail we have to discuss about boiling and condensation. So first in detail we will discuss about boiling part. So boiling means the liquid to which heat is supplied, and because of that liquid is converted into vapor of that liquid. So now at present we will discuss about boiling part. Whenever we are talking about boiling phenomena, we know that whenever the liquid is come in contact with the solid surface whose temperature is more than the saturation temperature of that liquid at that pressure, in that case heat is transferred by means of convection. And the boiling is also called as evaporation when the vapor pressure is lower than saturation pressure of the liquid. In that case, the latent heat for the phase change is taken from the liquid itself. That is, the example we can say is cooling of our body by sweat formation and drying of the cloth. But when the latent heat for the phase change is supplied from the outside, it is called vaporization. That is when we talk about a steam generation taking place in the boiler of the thermal power plant. So we can say that the heat supplied per unit area, that is Q by A, that is equals to small q, it is also known as heat flux, is depend upon excess temperature delta Te. So excess temperature delta Te, that is equals to surface temperature minus saturation temperature. So the heat flux Q, that is equals to H, that is convection heat transfer coefficient, into bracket surface temperature minus saturation temperature. So the surface temperature minus saturation temperature is known as excess heat. So the amount of heat which is more than the saturation temperature of the given fluid at given pressure is, you can say, termed as excess temperature. The boiling process has lot many applications. Some of them are mentioned here. First, heat absorption in the refrigeration and air conditioning system, production of steam in the nuclear and thermal power plant, drying of the food and materials, spacecraft and rocket, where heat flux is very high, that is in order of 10 power 2 megawatt per meter square. This boiling process involves formation of bubbles at the solid liquid interface. Then these bubbles that will grow, that will detach, and that will move in upward direction. It depends upon the property of liquid, what is the value of excess temperature, and what is the nature of that surface. The boiling can occur in the various conditions, like first is pool boiling. So it occurs when the heat transfer is due to natural convection, that is we are not using any external agency for mixing. The mixing takes place due to bubble growth and detachment. Second is the forced convection. So in this case we have to use some external agency for movement of the fluid, and the heat transfer takes place by forced convection and mixing. The third is, you can say, subcooled or local boiling. So in case of the subcooled or local boiling, the liquid is below its saturation temperature and the bubbles are formed and condense into the liquid itself. And if we talk about next part, it is a saturation boiling. So in case of this saturated boiling, the temperature of the liquid is slightly above the saturation temperature. The bubbles form will move towards the liquid interface, and the liquid is, or you can say the bubble, that will move in upward direction due to buoyancy force. Now, to conduct the experiment on boiling, platinum wire is inserted in the pool of water. An electrical supply is given to the wire to increase its temperature. In case of pool boiling or in case of forced convection boiling, 6 different regions are available when we increase the heat flux. The different regions are shown in the next slides, where the heat flux is plotted against the excess temperature. So on x-axis you can say excess temperature is available, and on y-axis heat flux in terms of watt per meter square is shown. Now one by one we have to discuss all these 6 regions. So first we will discuss about a free convection boiling, that is region number 1. So in this region number 1, the liquid near the wire gets slightly superheated, and it's that superheated liquid moves slowly into the liquid vapor interface due to the density difference, where evaporation of liquid takes place. In this case, the excess temperature value is not more than 5 degrees Celsius. You can see point number A, and this is shown in, you can say, next slide with the figure number 2A. So now we will refer figure number 2A and what is there that we are discussing. In the figure number 2A, you can see when the temperature difference is very less, the liquid which is in contact with the platinum wire, that is at higher temperature, and the other side liquid is at lower temperature. So there is exchange of heat takes place because of natural convection. The bubble will form, they will detach, and they will submerge in between. So now we will talk about the second part, that is onset boiling, where you will find 2 or 3 small dots, that is a bubble that will form, and they will try to move on the liquid air interface that is on the top of the surface. Now we can see in the figure number 2B and 2C, we will observe that the bubble will start to grow, but as the excess temperature is less than 30 degrees Celsius, so what happens is the bubble will detach from the surface. They are moving in upward direction, but they will condense in between, and it is called unstable nucleate boiling. So the bubble will not reach to the upper part of the system. Whereas when we'll talk about the next figure, that is figure number 2D, we'll see that now in the figure number 2D we can see that when the excess temperature is more than 30 degrees Celsius, we can see that there is a continuous formation of bubbles. The bubble will grow and they will detach, they will move in upward direction, and the cold water or cold vapor, the cold liquid, that will take care of that vacant part, and again they will reach to the platinum wire, and again the bubble formation will start, and that bubble formation is continue, and this part is known as a stable nucleate boiling. So in this part, in the stable nucleate boiling, we'll observe that the amount of heat flux which we are supplied is maximum one, and in that case the heat transfer coefficient is very high. Figure number 2E talks about transition film boiling. What happens in that case is, when the heat flux applied is very high, in that case the excess temperature is between 30 degrees Celsius to 120 degrees Celsius. In that case the rate of formation of bubble is very fast, and it will form one film over the wire which will resist the cold fluid to come in contact with the wire. And because of that you will observe that there is a sudden drop in the Q value, that is heat flux, and we will observe that excess temperature is reached to point number D, where we will observe unstable boiling in that case. Now we are referring figure number 1, that is the graph of temperature excess versus heat flux, where what we had discussed, all that thing will be observed. So first part is a region where free convection is observed, and that is region number 1. Then you will observe nucleate boiling, that is region number 2 and 3, where you find point A, B, P and C, where critical heat flux is available and excess temperature is around 30 degrees Celsius. Then when the heat flux is increased, you can say we are moving towards the transition zone, that is in zone number 4, where the excess temperature is between 30 to 120 degrees Celsius, and we are moving from point number C to D. And after reaching to the point number D, we will observe that the film, which is vapor blanket that is formed over the wire, is not allowing the fresh liquid to come in contact with the wire, and excess temperature is more than 120 degrees Celsius. Then the heat transfer through conduction is takes place, and that is called stable film boiling. With increase in the value of excess temperature, the heating surface become bright and thermal radiation from the surface become predominant. Graph, when we see the graph in the figure number 1, 8 point C, we will observe maximum heat flux is reached. It occurs at around excess temperature of 35 degrees Celsius, after which the heat flux start to decrease. This heat flux is called as critical heat flux, Q critical, and the excess temperature is called critical excess temperature, delta TE critical. At this point, the temperature may exceed the melting point of wire, and thus it is also called as burn out point. So what we had discussed till this point, same thing is mentioned here. Just go through the description and then we'll go ahead with the next part. What is there in the region 5 and 6, what is the critical heat flux, what is the burnout point, all that theory is mentioned here, and we had discussed that part. So again, please go through the description. So that was all about boiling part, basic fundamental things related to boiling. Now we have to discuss about fundamental of condensation. So what we know is condensation means when the vapor is converted into liquid, it is called condensation. And here we are talking about rejection in terms of latent heat. And when there is a rejection of latent heat, we will observe that the vapor that will convert into liquid, and we have to discuss about that condensation part. Now condensation is reverse of boiling. When a saturated vapor will come in contact with the surface whose temperature is lower than saturation temperature of that substance at given pressure, the vapor will release the latent heat, very important, latent heat, and change of phase form from vapor to liquid immediately. This process is known as condensation. There are two different type of condensation processes. One is called film-wise condensation and second is drop-wise condensation. So in with next figure, we will discuss what is called film-wise condensation and what is called drop-wise condensation. So at present, just refer what is mentioned here for film-wise condensation. Figure number 6.1 is talking about film-wise condensation. So in case of film-wise condensation, the liquid wets the surface and continuous film is formed on the surface. The film moves down due to the gravity and the thickness of the film increases progressively due to addition of condensed vapor. This film offers thermal resistance to the heat transfer between surface and the vapor. The heat transfer will be now due to the convection between the film and vapor and conduction between the film and solid surface. So you can say conduction and convection, both the things are available. Thus the overall heat transfer coefficient U will be very lower. The film condensation takes place when pure vapor condenses on a clean surface. The best example which we can consider is during summer season, if or particularly during monsoon season, if a plastic bottle is filled with the cold water, immediately we will observe that the vapor blanket will form on outer side of the water bottle, and what we can see is okay, the film will form and slowly the film that is moving in downward direction, or you can say film that increase progressively because of the condensate vapor. To the figure number 6b, when the liquid does not wet the surface and the vapor condensate in form of droplet, it is called dropwise condensation. On the solid surface, the droplets will be formed and they will fall gradually in the downward direction due to gravity. The droplets are formed in the cracks and pits on the surface. They grow gradually in size, break away and finally run off the surface, taking other droplets. Here no film is formed between the vapor and solid surface. Thus heat transfer coefficient is very high in case of drop-wise condensation compared to the film-wise condensation. It is always desirable in the industry as well as in the real life application about droplet condensation, but it is very difficult to achieve in regular practice. For designing the condensing equipment, always film-wise condensation is considered. Drop-wise condensation can occur only, this is now very important, drop-wise condensation can occur only on highly polished surface or by certain activities like fatty acid, silicon extra in the vapor, or you can say when we apply butter or you can say silver surface is available. In that case we can create a drop-wise condensation. However, still there are lots of problem in obtaining drop-wise condensation. So even though drop-wise condensation is highly desirable, it is very difficult to achieve in practice, and generally we prefer drop-wise condensation over film-wise condensation. Again, this fundamentals of boiling and condensation is considered from the book Heat Transfer by Dr. Alpesh Mehta and PG Choksi by Books India Publication, Ahmedabad. So stay with us. Have a good day. Thank you.